Hello everyone and welcome to this tutorial for the Data-Driven Portfolio Optimization course focusing on machine learning for portfolio construction. Today we're gonna focus especially on random forest just because the whole machine learning field applied to portfolio it's rather broad, so we would need a whole course to deal with it. So we will focus on this only model that is easier to explain and we don't need that much background. First, we give a little bit of general definition on machine learning. What is machine learning? Well, machine learning is this branch of computer science that studies algorithms that are not hard-coded, but rather they are learned from the data. They learn these patterns from data and they will make some predictions, and on these predictions we will get some feedback which we will use to update the model, right? They are data-driven, they are adaptive to new data, and they aim for generalization. They want to be able to predict unseen data. Also, we want to introduce supervised learning because this is the type of machine learning that we're going to use today with random forests. And supervised learning consists on having labeled input and output pairs. And with this label input and output pairs, we want to learn an obscure function. Let's put an example of that. Let's imagine a cat detector, right? We want to detect if an image has a cat or doesn't have a cat. So we would have a lot of inputs, a lot of images of cat, and a lot of outputs, which will be labeled yes or no, if the cat appears on the picture or no. And in our minds, we have this obscure function that once we see the picture, we are able to determine if there's a cat or not in the picture. So yeah, there's this obscure function f that you see here on screen. And with supervised learning, we want to approximate this function using these input and output pairs in a way that we can actually code mathematically. So yeah, we will approximate this function with this f of theta that you see here. There's two main tasks that supervised learning wants to solve. First one is regression, so we want to predict a numerical value given some features. You have an example here on screen. You can predict a house price given number of rooms, postal code, and square meters. And there's also the classification problems where instead of a continuous number, you want to predict a discrete number. Also here you get an example of a patient that has diabetes or no, given some features, right? But yeah, the example of the cat is also a classification task. Then we want to ask ourselves, how can we use machine learning in portfolio construction, right? So basically there's three main ways to do that. First one is to predict the inputs of the portfolio optimization problem, right? So we still keep our portfolio optimization problem, and with machine learning we will just predict either mu or sigma or both. And this is the first way that we can use machine learning. Second way is portfolio guidance in a way. So we put the two examples here on screen. One is filtering your investment universe. Imagine you have like a large investable universe, a lot of assets that you can invest in, and you want to reduce it a little bit and make a subset of these assets. Well, you can do that with machine learning. Another problem within this guidance task that you can do is detect market regimes. So imagine that now you have a perfect machine learning model that detects if we're in a bull market or in a bear market. Maybe we want to change portfolios in order to control risk more or less. So this is also something that we can do with machine learning. And finally, there's this other task which forgets about the original portfolio optimization problem, which is the end-to-end task. So there's some machine learning system that will predict and will construct the portfolio directly. Here we see a little bit of reinforcement learning involved. There's also some supervised learning involved. But yeah, these systems we will not treat. We will treat the systems where we keep the portfolio optimization problem. And the thing is, why do we want to keep this portfolio optimization problem, right? Why we want to fuse machine learning with traditional portfolio optimization? Well, domain knowledge is king, right? In any information system, the more domain knowledge that you can use, the better, right? The better predictions that you're gonna do. And since there's like decades and decades of financial theory behind portfolio optimization, including this, it's rather a no-brainer because it will improve predictions a lot. Also, optimization is well defined and we can actually include constraints as well, so we can control some of the things, specific things within a portfolio, right? So specific variables, specific metrics we can control. With machine learning is a little bit more obscure. It's a black box in a way, so it's more difficult to interpret, it's more difficult to put constraints on, and with traditional portfolio optimization, we more or less know what's going on because we define the portfolio optimization problem ourselves. And finally, yeah, the other reason is that if we have a system and we can improve just a bit of the system, it's going to be better than trying to improve the whole system as a whole. But yeah. And today, as we said, we're going to focus on random forests because, yeah, we have limited time. We don't have time to treat all the machine learning problem because it's a really, really huge problem applied to portfolio optimization. But instead, we're going to treat random forest. And even though it seems that, yeah, this is a really old model, right? This is still used or no? Well, actually, from my experience in the industry, it's still used. It's rather important still. It's really, really, really useful for overfit, right? It's one of the models that overfits the least, and this is quite important as well in finance. And also we have this intuitive concept about random forest, which is we have a lot of opinions, right? Like random forest, we will see later how it works, but we can interpret it as like being in a financial firm and having a lot of analysts giving their opinion on something. So yeah. But before explaining random forest, we have to explain what decision trees are. Decision trees are the foundation of random forest. That's why we gotta start by this. What is a decision tree? Well, a decision tree, you can see in the screen some nice flowchart. And yeah, a decision tree is that is a flowchart that uses features to split the prediction, right? So here you see an example on this on the screen. You see we want to predict what kind of fruit we have given, like we give a fruit and we want to predict what kind of fruit is that, right? So this flowchart would follow, right? Would be, is this fruit red? Yes or no? And then depending on that, we can ask for the weight later, or we can ask for the maximum length. And depending on the values on each of these features, we can actually finally predict which kind of fruit we're dealing with, right? So yeah, this is a decision tree, and there's a systematic way to build these decision trees from data. And the way that is done is using recursive partitioning. And yeah, basically how we do it is we analyze for each possible split, we analyze the split that will increase separability the most. We can quantify that with Gini impurity. You can see the formula on the screen. You can also minimize entropy, but here what we use is minimizing Gini impurity. It's this formula that you see here on screen. And what we do is we take all the data and we look for all features and for all possible split points of each feature, what split point and feature is gonna decrease Gini impurity the most. And then we do the partitioning there. And once we do the partitioning there, we get two child nodes and we do the same, right? We iterate through all the features and through all the partition points for all the features. And then we see which one is gonna decrease Gini impurity the most. Decision trees can overfit a lot. If you give an unlimited decision tree to your data, in the end, all your data is gonna be split, right? And all your leaf nodes are gonna be a single data point. So we want to control overfit in a way, and to do that we have hyperparameters, right? We can use the hyperparameter of maximum depth, that is the number of splits, like the number of levels that you can get on a decision tree. You can also quantify minimum samples per split, right? So at each split point, how many samples do we need in order to allow a split from that point? Or we rather consider this point as a leaf node. This is another hyperparameter that we can consider. There's also another hyperparameter which is the minimum samples per leaf. So yeah, this basically is what the name describes. For each leaf node, how many minimum samples do we need to have in order to consider that a leaf node? If not, we would go back to the previous split, to the previous node. And finally is the minimum impurity decrease. So yeah, at each node we consider, hey, if we split here by the thing that minimizes Gini impurity the most, what's the difference between Gini impurity before and after the split, right? And yeah, we can also control that, and we can say, okay, I want a minimum here, or you will consider the first node to be a leaf node, right? And we can tune these parameters via validation, right? We can use cross validation, some grid or random search, but yeah. One example of the decision trees applied to the portfolio problem. This is a guidance task, right? So yeah, we want to predict if from a universe of stocks, each individual stock is gonna be either a good or a bad stock, and good meaning it will have a positive return next year, but it will have a negative return. So yeah, all of these stocks, they will have a lot of features. We can calculate it from time series data, or maybe we get features from some data set, external data set, right? Some categorical features or some features that are not part of the time series of the price data of the stock. But yeah, features like the price to earnings ratio we can consider. Is the stock price to earnings smaller or bigger than 15, right? Is the momentum smaller or bigger than 5? Yeah, we can consider different factors, different split points, also categorical split points, as you can see. And yeah, the way that this goes is the construction goes the same as before, right? We start with all stocks at the root, and then we select the different features at each point that maximizes separability, right? That minimizes the Gini impurity. Decision trees are not perfect. They have pros and cons, as most machine learning models. The pros of the decision tree is that they are really, really easy to interpret, right? You can see the flow chart. It's really easy to determine why this model makes some prediction or makes the other prediction, right? You just follow the flow chart. It also handles different data types. It handles numerical, categorical. It could handle other kinds of data, like maybe images if you find some way to split the images, right? If you find some split point. It also has a compact representation. It's not like LLMs. You have to store billions and billions of parameters and you need a lot of space. No, here it's just a simple flowchart that you have to store, and also it's really, really fast. It's a really fast predictor and makes really fast predictions. The cons: it has a really high variance, right? And it tends to overfit a lot. That's why we tune the hyperparameters, but even though it's really easy for these models to overfit, it's also really unstable. So if you change a little bit the training data, it will change a lot the predictor. This is something that also happens with decision trees. It has some bias and it tends to split features which have a lot of different categories or a lot of different split points. So it will focus on these rather like broad features. And also it has a bad probability interpretation. This model either like gives 1 or 0, right? So you don't actually get a probability interpretation out of this model. To solve all these problems, we can use ensemble learning, we can use bagging. But yeah, the basic idea is, if I'm in a group of people and I ask, hey, how heavy is a cow, right? No one really knows how heavy is a cow. Maybe someone is a cow expert, right? But like, no one really knows how heavy is a cow. So maybe something that I can do is, hey, you, how heavy is a cow, right? Ask one person. And person 1 will say 1,000 kilos. Person 2 will say 500 only. And person 3, let's say, it will say 600. What's the average of that, right? The average of that is going to be closer to the real value, which in this case, I looked before recording this video, but the average is 700 kilos. So yeah, whenever you want to do a prediction and you ask a lot of people, the average tends to be closer to the true value than it tends to the true value, right? The average. And this is the idea of wisdom of the crowd. If you ask a lot of people and do the average, normally you can get a good estimate of that. So yeah, we can use this idea with decision trees, and we can combine a lot of these decision trees for prediction. This is not only done with decision trees. That's why it's done in ensemble learning. We don't consider first like decision trees, and yeah, this is how it's done. What we do is we bootstrap, aggregate different predictions in a way that it makes sense, right? For instance, in classification, we will aggregate via voting, right? So we have a lot of predictors, and we will say, okay, what's the majority vote, right? So we can take the majority vote, the class that has the most votes out of all the predictors, and in regression we can take just the average, right? What do we need for that? We need really fast predictors, because we're going to use a lot of them, and we need high variance predictors because we want a little bit of like difference, right, between them. So for that, decision trees are perfect. Yeah, they are really, 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 really good for that. How does this bagging work exactly, right? It's just we create a lot of predictors and, right? No, because if we create 1,000 decision trees with the same data set, they are going to be the same tree in the end, right? We want some variation, and we will use this instability of decision trees to generate a lot of different decision trees. What we will do, right? whenever we train a decision tree, we train with a dataset, and a dataset of points with a lot of features, right? Yeah, here what we do is, if we want n decision trees, we will train it with n different datasets. How we will get these n different datasets? We will get these different datasets from the original dataset. So we will sample these points with replacement to create the new datasets, right? So the new dataset will have the same amount of points of the original dataset, but sampled with replacement from the original dataset. What does this mean? This means that the points on the new dataset sampled from the original will have some repetitions, and some of the points will be missing, right? Because, yeah, if some repeat, they don't leave space for all of them, right? So, yeah, we can sample new datasets this way, and we can create a lot of datasets this way by sampling with replacement from the original dataset, and then basically we can create a predictor for each of the new datasets, and these predictors will be slightly different, and we'll have some variance that we can use for our final predictor. So yeah, this is how we do it. We train these, let's say, n predictors from these n new datasets sampled by replacement, and we aggregate, as we said before, classification. We do some voting. We can do majority voting, or we can say 2/3 of the votes have to be this class in order to predict it. We can define a little bit the threshold, or we can do regression, and we do average. We do like, yeah, like some aggregation we can do. And yeah, basically using bagging, but with trees we get random forest. There's a little technicality extra, right? For random forest. Random forest, apart from using bagging with decision trees, they make them a little bit random. That means that each tree will only have access to a subset of features from the original dataset. So this adds a little bit more randomness to the mix. And of course, like, if each individual predictor has a little bit more variance, then we get a better prediction in the end. But yeah, here on the screen you see also a formula that determines, like, that shows the variance of the whole ensemble, right? Aggregating everything, it's gonna reduce variance by a lot, and the way it does is, yeah, this row that you see here, this is average correlation. So yeah, basically you see that the correlation will decrease quite a lot, right? Because this average correlation absolute value will be between 0 and 1. So yeah, this value will decrease, and yeah, the variance of the ensemble will be quite low. Once we have a clear idea of what random forests are, we can see the benefits of this bootstrapping of decision trees. The one that we talk about is variance reduction, right? So as we can see from the formula before, the variance of the final prediction is reduced by a lot. Also, we get like implicit outlier handling, just because the outliers will appear only will only be on some of the predictions, right, from the individual predictors inside the random forest. So they will get averaged out. So we will eliminate them via averaging, and finally we will improve generalization a lot. This of course reduces overfit a lot. We can tune some things as well in the random forest, that is the number of estimators. This is something quite important in a way. As you can see from the formula before, the variance gets reduced. There's a factor of n of how much the variance is reduced. And yeah, if we keep increasing trees, we expect the predictor to be better and better and better and better, right? If we keep increasing the number of decision trees within a random forest, we expect this random forest to perform better. The reality is different. It's a little bit different. Is that at some point we reach a plateau, and it doesn't matter how many more trees we add, the error is gonna be similar. And this is what happens when you plot the error of a random forest given the number of trees. You always see some kind of like graphic like this, that it goes down rather quickly and then it reaches a plateau. Here you see that around 150 or 200 you already reach a minimum, and this is mostly noise at this point. Also, yeah, decision trees have pros and cons. Random forests also have pros and cons, right? The pros, they have really good performance. Actually, they are really robust to overfitting as they average out. They are really fast to train because you can parallelize all the training of the individual decision trees, right? So you can do it in parallel, and it can get really, really fast. They also handle data types, same as decision trees, right? Numerical, categorical variables, no problem. And also you can get some feature importance in this from this random forest, right? So once you have a random forest trained, you can actually go inside and see what's the importance of each of the features on the final predictor, on the final prediction. So this is something that you can actually tell in your dataset which features are important and which are not. Cons: this is less interpretable than decision trees, of course. You lose a little bit of the notion of like the diagram. Yeah, you can go inside in each of the individual predictors, but in the end, as it's averaged out, there's not a clear flowchart that you can follow, right? And the performance might be limited, especially for high dimensional data. For high dimensional data, neural networks might work better, but yeah, this, to be fair, this is a really old model, but is still used in a lot of cases. So yeah, especially for low dimensional data, it's quite useful. One example for the portfolio optimization problem using random forest is this stock screen that you see on the screen, and that later we will treat with the code that you will see later. And basically what we want to do here is identify stocks that are likely to be top performers. We will select the ones in the top quintile, given top quintile as top 20% of stocks for the next year. So yeah, how can we predict that, right? We can predict that without random forest. Just we do the sample mean and from the previous year, and we see which stocks are on the top 20, and we say, okay, maybe these ones are gonna still be on the top 20, but the sample mean is quite noisy, right? So what we can do is, instead of using the sample mean to predict these top stocks, we can use the annual reports of stocks, right? Public companies in the United States especially, but yeah, all around the world, but we will focus on the United States companies. They have to report annual reports at the end of each year with a lot of features. They have to report how much debt they have to report their inventory, they have to report research and development expenses, they have to report a lot of things, right? So why don't we use all of these reports to predict the top performance for the next year? Well, we can do that, right? We just have to use historical data and label which stocks have been the top performers, top 20%, and which haven't been, and just train a random forest classifier with this in order to try and learn the patterns between the annual reports of a previous year and their performance on the next year, right? So this is doing some kind of value investing, like all these investors that they look at the fundamentals and they say, okay, this stock is going to be good, this stock is going to be bad. We do the same, but with random forests. We can just train this random forest to predict the probability of a stock being a top performer. The probability interpretation of a random forest we can use as like how many decision trees vote yes and how many decision trees vote no, right? And do the proportions. And we can select a threshold if we want, or we can do majority voting. In this case, we can select a threshold that we need more than 70% of votes to say that stock is in fact gonna be a top performer, right? Maybe we want to make sure that we're not mistaken. That's why we ask this threshold to be higher. And then after we get this predictor, what we can do is just reduce the huge universe of stocks that we have. We can reduce it to a smaller universe of stocks, and then in this smaller universe we can apply some portfolio optimization, right? The kind of portfolio optimization that we wanna perform. Why do we wanna do this? Maybe it's too much data for the portfolio optimization problem. Maybe we don't have that much resources to get as many data. So if we reduce the data set, then maybe we have enough money to buy this data. This is also a possibility. Yeah, sometimes it's interesting to reduce the universe of investable assets a little bit. But yeah, so yeah, we will see this later on the data. How can we combine first random forest, and once we have the predictions from random forest, we will just reduce the original data set to the top performers, and we will apply portfolio optimization to these top performers. Finally, I want to talk about also boosting. We talked about bagging, but there's also another ensemble method which is boosting. And previously with bagging, we saw an aggregation that what it does is it focuses on variance, right? It focuses on reducing variance. In this case, boosting will focus on reducing bias. the way it does this is quite simple. It will first train a simple predictor. We can say decision trees as well. We can say perfectly decision trees, and then it will see which original data points fail on this predictor, right? And the ones that fail on this predictor are gonna help training the next stage of predictor, right? So we're gonna train a new predictor focusing on those points that failed on the previous predictor. And we're gonna do this sequentially. So on the second predictor, we're gonna train focusing especially on these points that failed on the first predictor, and then we're gonna train a third predictor focusing on the points that failed on the second predictor, and we're gonna do this iteratively until we have enough predictors, until we decide we have enough predictors, and then we can aggregate the prediction of all of these predictors in order to have a prediction that will reduce bias. Why is it reducing bias? Well, basically we penalize all these predictions that are wrong, right? So we focus on being right all the time, right? We focus on fixing the mistakes. So yeah, this way we focus on reducing bias. What can happen? This can introduce a lot of overfit, right? So maybe now if we change the original data, this data has been perfectly overfitted to predict perfectly the original data set, and with new data maybe the prediction is not so good. So it's quite challenging boosting compared to bagging. Bagging is quite easy to train. Boosting is a little bit more challenging, and yeah, compared to random forest, boosting is sequential, right? It cannot be trained in parallel. It needs to be trained sequentially, so training times are a little bit higher, and it focuses on bias instead of variance, which random forest and bagging methods do. And yeah, it can achieve higher accuracy, but it is more sensitive to outliers and to noise. It overfits more. So yeah, we need to regularize a little bit. We need to be more careful with boosting. Bagging is a little bit easier to train. But yeah, in this slide, yeah, we can see the summary and takeaways of this theory part of the tutorial. And I also prepared a Python notebook in order to interact a little bit with this concept of using random forests and decision trees for the portfolio optimization problem. So this is the notebook I've prepared for you guys to practice these concepts that you just seen. And yeah, basically this notebook is quite structured already. It has some code snippets that are missing, some to-do parts, and you can actually practice your portfolio optimization skills here. They should be quite easy, quite easy. And you feel free to use this notebook as a base for anything else that you want to do, or just execute it and just to practice the knowledge that you just learned. But yeah, let's quickly go over to the notebook. You can take a look later if you want, a further look, but let's take a first look. So first, what we need is some data, right? So you can get the data from these links here. This is my personal links. So this is already pre-processed data from Symfin, but I pre-processed myself, so you can actually access it here. And this is 2016 and 2017 data. These are the annual reports actually. This comes from the cash flow, the income, the balance sheet, and the income statement, right? So these three main documents, right? And yeah, basically first you load the data, then you can visualize this data. You can visualize returns, right? Let's visualize returns of all these stocks in this universe that they have like public annual reports, 2016 and 2017 data. We don't see nothing really unusual. We can also visualize all the features in this data set. You can visualize here research and development, inventory, debt, dividends paid. There's a lot of different features that we will later use for the random forest, right? We can also look at the correlation matrix between features, right? You can see, yeah, let's see if I can, yeah, make it bigger, right? And you can see this correlation matrix. There's a lot of features, and maybe some of them they are really correlated. So we do also a pre-processing step here, that is removing pairs that are highly correlated. So the random forest will work with less variables. It shouldn't be a problem, but still we can do this, right? So this is a lot of code that what it does is basically this. It will remove pairs that are highly correlated, right? On pairs that are highly correlated, only one of the two elements in the pair will remain and the other will get eliminated. And as you can see, we reduce a little bit the amount of features, but it's still a lot of features, right, that we're using. So yeah. And then first what we do is we can use the historical data of returns in order to quantify, to put the labels, right, into the different stocks. So first we see the stocks that have like top returns, and we see the stocks that don't have top returns, and we can label them this way in order for the random forest to be able to do classification. And yeah, we do the train and test split. This is really important bit, and it has to be quite thorough, just because we don't want any data leakage. We don't want to have some look ahead bias, right? So we have to take we have to take care with this one. But yeah, this is the train and test split. We also perform cross validation to select the hyperparameters of the random forest and the decision trees later. But yeah, first we treat the decision tree problem, and we see if this decision tree can predict actually top performing stocks and non-top performing stocks. And here we plotted the tree, right? And this is what we talked about before. It is really interpretable. You can actually take a look into this and see how this tree does the classification, right? How is it able to say if a stock is top performing or not? I think top performing, depending on how you define these two, right? But top performing should be class 2, right? So here you can see the class 2. How can we tell if a stock is top performing? Well, we can follow a little bit the diagram until class 2 and see what it does. Yeah. And also later we can move into random forest. Once we move into random forest, we can do the same, right? We can just perform cross validation, and we can see the error, the cross validation error. You can see the accuracy is not that good, right? This error is used with accuracy, and taking into account that we're just predicting the top 20%, it seems that a dummy predictor would be better. But then we will take a look at the recall and precision and see that actually it's doing something, right? This predictor is actually doing something, even though on accuracy it seems that it's not doing anything. And yeah, we can tune this random forest. We can use the same plot as you saw on the theoretical part on the presentation, and yeah, we can basically select the number of trees. We can select voting levels. We can select a lot of things, and later we can plot. We can perform cross validation and see recall, precision, and classification rate. As you can see, classification is 80%, so it would seem like a dummy predictor would be better. But then once you take a look into precision, it's better, right? Once you take a look into recall, so recall is not that good, but we focus a lot on precision on this case, and precision is quite okay, taking into account that we're just using like a 20% and 80% split, right, on these levels. So precision is quite good actually. And yeah, then we can also first we're just doing some cross validation, but then we can train a final predictor using the full training data, that's 2016 data, in order to predict 2017. So once we're done with cross validation, we can actually predict, use the whole data to predict 2017. And yeah, once we have this predictor, we can just apply this predictor to select the top stocks from our universe and get our reduced universe. And once we get our reduced universe, that's all we need from random forest in this case. We can already perform backtesting and see how it performs, right? Here in this case, we perform backtesting using monthly rebalanced mean variance portfolio, and we can also test equally weighted portfolio. So this equally weighted would be top quintile as predicted by the random forest, and let's see how they perform. So yeah, we can select all the stocks and then just get the specific ones that the random forest says that are top performing, and then we can download this data from Yahoo Finance. Actually, some of the data we cannot download because either stocks have been delisted, or they have been their ticker has changed, or yeah, there can be multiple reasons why we cannot download these stocks. So in order to not introduce a little bit of survivorship bias, right? Because it would be like, yeah, we remove all the stocks that have been delisted. No, this is not how we work. We will remove all the stocks that have been delisted or we cannot fetch, right, before the backtesting starts. And here we start the backtesting in May. We will start it. So we remove it according in April. Sorry, we start, and we remove all the stocks according if we can fetch the data on the day previously to the backtest, right? And we start the backtesting on April because the way that public reporting goes in the United States, companies, they have around 3 months to report, right, after the year ends. So in a way, we don't want to use data from the future. So we are using just data once the reporting is available, right? That's why we start the backtesting on April. This a little bit of technicalities that we have to take that we have to be really careful if we don't want to make any mistakes on the backtesting, right? But yeah, basically there's a lot of stocks that fail to download from our reduced universe, but we still get a universe, right? And yeah, once we get a universe, we can actually we can download all the data. We also download S&P 500 data, I mean the index data, just to compare, right? And yeah, basically we perform this backtesting, and in the end, after all the plots and everything, we can plot the backtesting between the Markowitz portfolio, this mean variance portfolio using the selected stocks by the random forest, this equally weighted portfolio on the top quintile. Here you see 1/n, that is 1/n over this reduced universe, right? So this is like top quintile as predicted by the random forest, and then you also see the S&P. The performance is much better, right? But it's much more volatile and much riskier, just because we're dealing with like less stocks, right? So as we're dealing with less stocks, the risk will be higher, but the performance can be higher as well. In this backtesting in particular, it performs really well. It doesn't need to, right? But in this backtesting in particular, this method of selecting the top stocks with a random forest and then using them for portfolio optimization, it works quite well, even though it's quite risky. And yeah, there's not much backtest done after 2017. You can feel free to do 2018, 2019 and see if it actually is a good strategy or not. But from the looks of it, it's a promising strategy, but still there's a lot more testing to be involved here before declaring this a really good strategy. But yeah, that's all for today. I hope you learn a little bit about random forest and a little bit of how machine learning can be applied to portfolio optimization. There's multiple more ways that machine learning can be applied to portfolio optimization. But yeah, this is it. Thank you very much.